Thank you, Joseph. Well, thank you for inviting me. It's just a terrific day. The only thing is I have to give a talk. And I realize that one way or another, I seem to have promised 3 different topics. And I'll try to come through. So one of them, was life. Life of a mathematician. Can I just say life of a M? Whatever. Okay. So that's, I just think it's a chance to sort of think, well, and of course, this, what I'm saying would be true for other areas too. It's just interesting to think as you're making decisions about what to do, what seems important to looking back. So then my second topic is maybe a little bit. So it was I unwisely said calculus versus linear algebra. Okay, now I just want to say right away who wins. Linear algebra wins. Okay, I'll try to. Yes. I have to admit, I usually start if I'm teaching a linear algebra class by some discussion like this where I say, you know, I'm sorry for you guys, you had to do all that calculus, forget it, all now we go. And now then the third part is a problem about triangles. So this is really the math. And it's a problem I just started thinking about, and I don't by any means have all the answers. So I hope you'll find it an interesting question, and maybe even you could try some MATLAB experiments. So, because also I am a great advocate for MATLAB. I can never make the darn program run. I know in principle, but somehow it doesn't run. So anyway, okay. So life. What do I think about? As well, I think it's a wonderful life. Actually, let me just say right away that, and that's probably the most important word I could use. That you know, if you're thinking about becoming a mathematician, teaching. Research, some travel, like getting a chance to come here. It's just terrific. It's so much the opposite. You know, the image of a math teacher is maybe not entirely favorable. You know, like you think about this person who was looking for mistakes, and I think that's actually the opposite of what mathematicians do. I mean, the greatest pleasure for a mathematician is you're teaching something, and the idea gets across, and you think in your mind, hey, they got it. You know, they caught on to this idea. That's what you know. That makes your day, and another very nice aspect of mathematician's life and life of you know, professors generally maybe is the independence that you kind of when you wake up in the morning you get to think, okay, what am I going to do today? What am I going to do in that class? What problem am I going to work on? Who am I going to talk to and learn something more? It's like it's your life. You get to choose, and that's sort of precious. I mean, you know, most jobs you kind of tend to be told what to do, and this sort of this happy combination of having something important. The teaching is important. The research is important. And then another really nice aspect is, like, I'll use just today as an example. So I came this morning, and, you know, in lunch, talking to 10 of the faculty, 10 others, you know, you're immediately friends. You have a connection right away because you've done the same kind of thing. You've taught, you've tried to explain ideas, you've tried to think a little bit further on those ideas. It's very much shared and it's very international. You know, I mean, you immediately connect with somebody in Sweden, somebody in Japan, somebody in Singapore. It's and the chance sometimes to talk to those people, visit them, and anyway, you can see that. I'm going to put 100% on this. I mean, it's just. Are there any bad points? I guess I should reduce that 100 somehow. I will admit, okay, there is one thing I don't like, and that's giving grades. If I didn't have that, my life would be perfect. But having to decide grades, see, I mean, I tell my class at the beginning that I am not here to grade you. And, of course, they don't believe it. They're used to being graded and struggling. But I say I'm here to teach you. And sort of gradually during the semester, they realize that that's really the job as I see it. So anyway, grading is, it somehow may be necessary because it gives people some idea of, yes, I can listen to the lecture, but I have to actually be able to use those ideas, and then that gets those problems get worked on, and so it's you know, you have to do math. It's not a spectator sport. You know, you can't just sit and let it happen. You have to tackle it. So that's why I want to get on to a problem about triangles. Okay. So you know what I think about number 2, but why? I guess, well, of course, calculus. I mean, I wouldn't throw calculus out completely. But I just don't want linear algebra to be thrown out completely. And it's too often been the case that calculus is like you start with calculus 1, calculus 2, calculus 3, you're pretty exhausted. But I mean, it's like running a marathon of calculus. And then differential equations. And I just think that the ideas of linear algebra, the fact data, I mean, this is the century of data. If you do experiments now, whether it's medical imaging, whatever it is, gene expression data, you just get a ton of data. And typically that data goes into a matrix, you know, maybe, well, we could have a matrix of, well, say an example would be grades. Okay, so we have a row for every student, a column for every course, and in goes the grade. So you have a matrix of grades. And now what would you want to learn from that matrix, and how would you do it? So what I am giving here, just one among many examples in which a matrix is the natural structure. You know, there are other problems. So if I had to, I don't know if I've ever done this. Which areas use more calculus and which areas use more linear algebra? I'm open to, I'll put physics. Would you say? Physics, yeah. I mean, they've got differential equations and they integrate stuff, right? I mean, I think, yes. Okay, I'll put physics here just to give them a head start. Okay. And now what? Economics, where am I going to put economics? In the linear algebra side, yeah. Right. I'm a little shaky on putting that there because, you know, these financial, you know, we are in this middle of this financial meltdown, and some people blame it on mathematicians because for creating these very sophisticated instruments. But you know what those instruments are called, or what they're often called derivatives. So I blame it on calculus, right? Yeah. Right. All right. Let's get serious here. Now, what other statistics? That's certainly central here, and that's a major subject, isn't it? That is so easy to miss. I frankly don't know a proper amount of statistics, and it's just really a very important area. What else do we? What about engineering? What are you going to say for that? That's. Would you say linear algebra? I mean, both. Yeah, both. I mean, sort of engineering. Maybe. So I'll put engineering maybe in the middle here. So the truth is that a lot of engineering, I mean, the laws like Ohm's law or Hooke's law, all the sort of central laws that describe physical responses tend to be linear. I mean, that's the natural. In fact, that's the central idea of calculus, isn't it? To kind of find that tangent, find that linearization, to find the leading term, which is the linear term, and then there's a quadratic and a cubic and the rest of a Taylor series. But the central thought is to be able to do that. So I would say engineering, and then, so here go the linear approximations. So that really leads you to linear algebra. And then here are the cases that are, you know, or where you have large voltages, large deflections, large torques, and the linear approximation isn't working anymore. You know, you have a shock, something major happens, and then you're in the nonlinear regime, and fascinating things happen there. And so that deserves to be on that side. Yeah. Now another, I won't try it for a complete list, of course, but where shall I put biology or mathematics of biology? Where would you say? Lots of it nonlinear, because I mean, I guess, you know, where the response of you know, if I push at this thing or something, that wouldn't move much, and there'd be a linear response. But lots of biology of how the heart, you know, the mechanics of the heart, the mechanics of blood flow, fluid flow. So there's certainly lots of biology here. But then there's a lot of these things like the gene data. I mean, you know, to be able to understand what causes the illness, to be able to associate the presence or absence of genes with the disease that may be reflected there. That's really a part of statistics a little bit. Genomics, so maybe I'll just put genomics here. Yeah. And, okay. I mean, what would one conclude here? I think you have to say they're both very important. And I'm very happy if that if we reach that conclusion, that you need to know both. I mean, that's what I think really is the truth, and that's why I'm always sort of like saying, don't forget linear algebra, because what's the point of linear algebra? Linear algebra takes the simple idea of straight lines, linear relation like Ohm's law or Hooke's law, and moves it up to any number of dimensions. So that's sort of where calculus is about dealing with curves. Linear algebra is about dealing with, you know, like on this board, I'm only going to be able to draw 2 or 3 dimensions, but where you have many inputs and many outputs, and the simplifying assumption is linearity. And here, of course, as we said, the key point is that at that point, that curve is almost linear, and the derivative, the tangent line, tells you that linear part, the leading term, right? So anyway, I've certainly been happy to learn that BYU has maybe 8 sections of linear algebra. That's terrific. I mean, that's excellent. And I'm sure more of calculus, that's normal and proper too. But to do it right, you're doing all right. What else to say on that topic? Yeah. Just that, yeah. I'm really, I mean, so linear algebra, let me say just a little more. That when I learned linear algebra, it was extremely pure, extremely abstract. I had a Professor Iwasawa who wrote everything on the board perfectly, you know, absolutely exact. But a big part of the subject was missing. The part that I now see in so I'm involved with the SIAM, the Applied Math Society, and there you just see the uses of linear algebra all the time, just constantly. One presentation after another will bring out applications of linear algebra. Actually, mentioning SIAM reminds me of one thing that I wanted to say there. Can I go back to the business about life of a mathematician? Because I wanted to report one experience I had working with SIAM, because I had a time when I was very active with them. And it happened to be the time that mathematics as a whole was finally sort of speaking up in Washington. Like the American Chemical Society would have a big, actually a building, a whole team of people lobbying Congress for support for chemistry. The American Physical Society, the astronomers are terrific at that. I don't know if you realize the astronomers, there aren't too many of them, but they have the best pictures. So they get in the papers for, you know, they've discovered some other little deal way out there. And math, which is central, it's not so easy to make to present it. But anyway, in those years, which was maybe about 10 years ago, mathematics kind of got together, and the different societies, so the most important society is the American Math Society, the AMS, and then SIAM does the applied applications area, which is very active and growing. And then the MAA is a really good society, the Math Association of America, for college teaching. So those were the 3. And so we kind of got together and thought we would try to make the case that mathematics funding for mathematics was getting neglected, which it was. You know, grants to support research in math were not keeping up with these areas. So off we went. We were really, I just want to say, you have to imagine these few mathematicians going to Washington, right? We didn't know from anything. And, but you have an agent, like a lobbyist is really the best word, who gets, you get like 5 minutes. So I had this experience. So there's a, the House of Representatives has a committee of, committee on science, let's say. Science includes science and math. And a whole lot of people want to present. So you get 5 minutes. So what are you going to say about math that will have an effect in 5 minutes? And it's not so easy. You get advice from this professional person. So the professional person says, don't forget about asking for money. You know, the mathematician will tend to, you know, be friendly and say, how are you all? But forget about the $20 million that you're supposed to be asking for. Right, so they said, write it down, ask for that. Anyway, I had this happy experience. So you go in the committee room with this committee of the House of Representatives. So I meekly go in, wait my turn, and I looked up, and who was, you know, there are a few members of the committee there, not all, but some. Well, one of them was my student. So that was great. You know, he said, oh, hi, Professor Strang. So I felt, okay, I have the upper hand here. Anyway, then he went on to be a senator, Senator Sununu from New Hampshire. And he's still a good friend. So just like that, for me, that was just one more wonderful example of how there's this network, this link of people who have tried to learn these subjects and all of these subjects and more, and just, you know, they know what it is to really make that effort, and partly successful. Sununu was not a great student, actually. Yeah, the lobbyist said, did you give him an A? Well, I didn't give him an A. He didn't deserve an A. But anyway, we are friends anyway. Okay. Yeah. Now I'm ready for this third part, if you are. A mathematician thinks, hey, I can't go on without doing some math, right? Okay, so can I ask you a question about triangles? And maybe we can think together how to deal with it. Okay, so here's my question. I have no idea where this question came from. It just kind of popped up. So here's the question. So is a random triangle, and of course we have to think, what is a random triangle? But anyway, typical random triangle, more likely to be an acute triangle, or what's the opposite? Obtuse, right. Obtuse. Okay. So acute means that, so that would be an acute oops, is it? I don't know. It is? Yeah, you can see better than, yeah. So all angles, all less than 90 degrees. and then let me draw an obtuse one where there's an angle that's clearly bigger than 90. So like that. So that angle is an obtuse angle bigger than a right angle, and so that would be an obtuse triangle. Okay. You have let me ask you, when you visualize a triangle, if I say triangle, and you think of one, do you think of an acute one or an obtuse one? You think of a right triangle. Gosh, you're a borderline person. Right, yes, okay, well, that's true, you do. Right triangles are the outstanding ones. Yes, that's right. So there would be this borderline. Yeah, with I guess probability 0, probably, yeah, probably 0. But nevertheless, a lot of things we do are right on that line. Okay, but what was your thought? Because I've never spoken about this subject before and never asked. I heard acute. Maybe did I more than obtuse? Is that right? Acute. Yeah. Sorry. Average angle 60. Right. Yeah, that's the one thing we all know is that those angles. Can I call them alpha, beta, and gamma, or is that too mathematical? Yeah, alpha. Right. Alpha, beta, and gamma. Oops. Gamma. Okay, so they add up to 180, right? Okay. All right. So acute, you're saying, is the most. So, but now, yeah. Now I knew somebody put me on the spot here. What is a random triangle? Yeah. Okay, two. For lengths. Okay, so you're going to start with lengths. I could pick 3 points in the plane on a circle. That's true. So the question somehow doesn't, the size I can vary. I could take it on a circle. I could take 3 points in the plane, yeah? I could randomly pick angles, yes. That's right. So I could randomly pick, or I could say I could randomly pick 3 angles subject to this condition. So there would be only really 2 degrees of freedom. Or I could randomly pick 2 edges, yes, or points on the points. Fix 1 and pick 2, yeah. And to tell the truth, I don't know whether those different meanings of random would give me the same answer. I'll tell you what I started with. This was a bad idea. So I thought, okay, 1 edge, all right, whatever. Let that, so there has to be an edge, and we don't really care how long it is. There it is. And then I thought, okay, where could the third point be to make the triangle either acute or obtuse? So, okay, so I start with 1 edge, and I think, okay, what about locations of this third point? By the way, I'm not going to this isn't where I'm going to end up, because what's the story then? Where could the third point be that would give me an acute? Somehow in this strip, yeah, because anyway, a guy out here, that angle is going to be obtuse. So somehow this strip, and maybe even points close to here don't work, because that's a big fat angle, so there might be a circle. So all this is acute, and all this, and even this little bit here, would be obtuse. So what you're thinking, what would that lead you to think? Yeah, that would think you'd think the probability was 0, right? I mean, random choice, you got much more room there for an obtuse choice. So that's somehow, anyway, I just mention that because it shows how probability is a subtle subject, and I think to reach the conclusion that the probability was 0 I don't think is the right answer. Yeah, but what is that probability? Okay, so what do you so shall I leave that up, or better to clear it away? Leave it up? Leave it up for a little while. Okay, so what's better? Do angles? Yeah. Choose 2 angles. Okay. Yeah, so this is a way, or I could say choose 3 angles at random that add to 180. So so if after I've chosen 2, and there's some can't be more than 180, I can use the 3rd one to finish it out. So, okay, so here, think about it this way. I'm choosing 3 random numbers that add to 180. And the question is, are any of them bigger than 90, right? That's our question. I'm choosing 3 numbers that add to 180, and I'm wondering, what's the chance that one of them is bigger than 90? Okay. So, how am I going to draw a picture of the, let me put in 3 axes, and whoops. Did I am supposed to write on this, right? Okay. You mean my suggestion to erase that was an impossibility, huh? All right, a blue. Okay. All right, that's fine. No problem. We need an engineer here, but we haven't got one. Yeah, all right. Yes, right. I'll put Jasper's name below that. Yeah. Okay. Well. Okay. Well, who knows? So now let me draw an alpha direction and a beta direction and a gamma direction. Okay. So those are. So I'm in like X, Y, Z. Only I'll call them alpha, beta, gamma. Now tell me, where are the points? Where are the angles in this 3D picture that add up to 180? So what does that look like? So alpha plus beta plus gamma equal 180, or X plus Y plus Z, if that might be. We have to use linear algebra for now. We'll compare it with calculus. You can have a vote which is better. So we could call 180 1. Okay, right. Okay, so what? So let me, if it's like X plus Y plus Z equal 1, what's the picture for X plus Y plus Z equal 1? It's a plane. Okay, so it's a plane. So how will I draw that plane? So I've called them alpha, beta, gamma. Now I'll stay with that. But think of it just X, Y, Z. X plus Y plus Z equal 1 or 180. It's a plane. So what kind of where does the plane sit? So an extreme possibility would be where one angle is 180 and the others are 0. I mean, that would be a very kind of a poor triangle. But anyway, so that would be the extreme case where, I mean, that's the angle alpha, beta, and gamma very small, and then in the very, very extreme case here, it would flatten out, it would squash down completely. Okay, so that would be that one. or another of the angles might grow to 180 and this would shrink. So are you saying that those are three sort of extreme points. And now where are the rest of the points? On the plane, on this, yeah, so it's a plane, and it's sort of in the positive, because these are all positive angles, so maybe it's that. Okay, where this would be the point that triangle shows, 180, 0, 0. That's where it's all, the whole thing. And where's an equilateral triangle in this picture? Right in the middle. So some point right there would be, it's an equilateral triangle, and the middle point right there would be the 60, 60, 60 triangle. Right. Okay. 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 So those are three. That's what we've got to work with. So now I'm going to take a random point in that triangle, and I'll ask, is the result acute or obtuse? So what do I do now? Sorry? 3 to 1? Let's see. So where... Let me draw a picture of where the acute ones are. Where are the acute? So what acute means what? That none of these angles can pass 90. So maybe, is there sort of a, is it something like that? So the idea is that these guys, which include the 60, 60, 60, of course, now what would be some other things? So the idea is that these are the ones where nobody's past 90. Is that right? Nobody's gone past 90. So this part got washed out because that angle was bigger than 90. This angle was bigger than 90. This angle was bigger, and here all three are below 90. So where would be, for example, where would be a right triangle? 90, so a 90 would be in the middle there? Yeah, right, where 1 is 90. Yeah, do you think that's right? I mean, because this is the key, going to be the key if it works, that those are the acute. And then what, if that's true, what's the probability of the triangle being acute? 1 in 4. 1 in 4. I think that's the right answer. So 1/4 are acute, and 3/4 obtuse, I think. What if I do 3 points on a circle? Is the answer different? I'm not sure. It is? Oh, jeez. Oh, phooey. What if okay. So let me try it with points. So this was an angle-based approach that gave us a nice answer. So now if I try it with points, so let me try putting 3 points, maybe just anywhere. Let's see what that gets us to. Yeah, is that your thought? If we try 3. Okay. But basically, I'm going to, out of the whole space, I'm going to jab down 3 points. Am I safe with a circle or not? I'm sort of nervous if I don't know. I don't know. I mean, I could, I'm going to pick coordinates. Let me call this point x, y. And this point maybe a little bit bigger x, y. and this guy a really big XY. Okay, so that's, a notation has been invented with three possibilities. Right, okay. Okay, and now, so each of those is a random number. I mean, and they could be anywhere in the plane. So I have to tell you, this is going to lead to an integral that I got this far and couldn't do. It's because I don't know calculus, of course. Yeah, but so anyway, my friend said, okay, use MATLAB. Okay, so take a point in the plane. So he suggested let x be, do you know this command, randin, of maybe just 1? Yeah, so then y similar, then the other guys, and then the big guy. So 6 of them. Of course, he knows MATLAB, so he would never do 6 separately, but let's just play it safe. Okay, so that gives me these 6 random points. Now, where's it gone? Oh, yeah. Yeah. Now, how do I decide, what's a good way to decide if that triangle is acute or obtuse? That's right, that's what I have to do, right? I want to run this experiment, maybe I should do this 1,000 times, right? So I have 1,000 triangles. And now what's a test for a triangle to be, so I could, okay, yeah. So if I've got these 6 values, I can figure out this a squared, that length squared, right? Because it's that squared minus that squared plus the y squared. I could figure out that length, and I could figure out this length, and I could figure out this length. So I could write the MATLAB commands that would compute that length squared. Let me just put it in what it would be. So what is the length squared there? It's the difference in the x's and the difference in the y's, right? Right. Okay. And then, so I've got one of those there, I've got one of those there. So I know the length squared. Now, what's the test for the triangle being acute or obtuse if I know the 3 lengths? Take the biggest one, okay? Take the biggest one. So let's say this is the biggest one. So let's say c squared is big. How do I know if it's big enough to... Is that the test? So the test is whether c squared is bigger than a squared plus b squared. That's the test for obtuse. Yeah. Of course, that it could be that one, or it could be that one, or it could be that one, or it could be none of them. If the test failed for all 3, then probably acute. Is that correct, though? Why is that? Because a right triangle is equal, right? And then if I grow a little more, take the biggest one, yeah, yeah. And then, I think that's correct. Yeah. But do you think, okay, you take the, so if I have a right triangle, of course, yeah, let's just be sure. So if I have a right triangle and this is the c, I'll say c squared, and this is the a squared, and this is the b squared. Those are the squares of the lengths. So then that adds to that. Now let me make it obtuse. Let me push this one over a little more. Then c is going to grow, right? Yeah, I think that's, you got it. Right. So then, now what's our problem? We have to find the probability of that. Right? Is that what we want to do? I think it's going to get a bit messy. Because, first of all, so now I want to take, among all choices of these 6 numbers, I want to compute these squares, and then I want to test those things. Is that right? It's certainly, this is looking good, right, by comparison here. Okay, so all right, ready for calculus. Okay. So I have calculus like 6-dimensional integrals, right? So a dx, dy, d middle x, d middle y, d big X, d big Y. I didn't intend that this would show calculus in a bad light, but it's going to do that. Okay. And then I put in this c squared minus a squared minus b squared. But of course, I have to look at what those are. So, this is painful. Okay. X minus x squared and y minus y squared. And now I subtract the a squared might be x minus middle x squared and y minus middle y squared, and subtracting also the other guy. What is that one? Middle minus little squared, middle minus little squared. Okay. And now I'm using rand n. There should be, so statisticians, since we love this e to the minus, you're going to say, where does this come from? But I think anyway, I think this normal, do you know about normal distribution? Well, what's the key factor in that normal distribution? It's an e to the negative x squared. Okay. And we have here multivariate normal because we've got 6 normals. So I think we've got e to the minus little x squared on 2, e to the minus little y squared on 2, e to the minus middle 1. This is really worse and worse. Okay. Okay, got it. All right. Now, what am I doing here? I think I'm integrating, I'm trying to find the area, the probability. I think I'm integrating where this thing is positive. I don't, well, you see why I didn't get it. But let me jump to the conclusion. Okay, so I asked my friend, and I give him, now let me give him his name, Alan Adel. He's a co-author on a paper. So I said, integrate this thing over the region where it's positive. And what answer do I expect for this? I expect 1/4, because I believe that 1/4 of the time c squared will be the biggest and bigger than a squared plus b squared. And 1/4 of the time b squared will beat the other two. And 1/4 of the time a squared will beat the sum of the other two. And 1/4 of the time it'll be acute and nobody will beat the other two, right? Do you see, does that make sense? Yeah, so I believe, anyway, he did this integral. He integrated over in 6 dimensions over the region where this thing was positive, integrated away, and he got the answer 1/4. Wasn't that neat? I mean, like, wow. And maybe I won't try to say how he did it. But that's one way, and you maybe see different ways. So I've picked those 3 points here in space using a normal distribution. That's what brought in those e to the minus x squared things. And maybe I should be formulating this problem in another way, and maybe also getting the answer 1/4, maybe not. Yeah. So, do I have time to ask you just one more question? Just so, you naturally think, I mean, I guess the one thing about mathematicians, if you ask, if they learn something, the first thing they think of is generalize it, make it more complicated. So, I mean, it's not, you know, after you've understood it, then it's too easy. We got this answer 1/4. We have to think. So, what do you propose as a extension of this problem? So random triangle, acute or obtuse. What would you? How would you change to another problem, or is it better to quit while you're ahead? Actually, yeah, I think that's the best. Yeah, you could. I did this on the plane on the way here, so I just have to tell you. Take 4 points. Okay, so now with 4 points, the fourth point could come in like that, or it might go out. Okay. So do you know a name for this type of region compared to that one? Convex and non-convex, right. Yes, yeah, right. So that's called a convex region. So all the angles are below pi, and here's an angle greater than 180 degrees, and so that's a non-convex. Anyway, just a report. So just tell me again, if I have now 4 angles, instead of alpha plus beta plus gamma being 180, what's the deal with 4 angles in a 4-sided figure? You know that one? They add to 360, right. So now I have a problem just like that, where now I have a 4th angle. Oh, I can't erase, but I'll use blue. So X out that, 360. Let's just practice, see if I can erase. Yes, it goes away. All right. And this, what's another letter? Delta. Okay, delta. Okay. So now you ask, but do you see that the picture has gone up 1 dimension, right? Because now we have four axes. So instead of this alpha, beta, gamma, we now have a 4th direction delta. So we've got a tetrahedron, and we have to look inside for which ones would be the convex ones. And if it came out right, the answer was a half for that. Half of them turned out to be convex and half not. Okay. Let me stop there. Thank you very much for it. Yeah. In this one. I don't know. Yeah. I literally, this is just something to think about. Let me put my email address. That's the most important, because people will have ideas, and I'll be glad to get them. So it's just gs@math MIT edu, right? Just like BYU, but yeah. Okay. Yeah, you'll have thoughts. That's fine. Oh. Oh, that's all right.
Just have them sign it, take them down. We'll sell them on
Are they ever going to erase?